A lot of announcements I just posted. I was going to go over those. Maybe I'll do them again at the end of the class if we get some more people join us here. So for those here, those watching, we still have a couple of things for this class. I've had some questions about due dates and stuff. So don't forget assignment 6 that was posted before Thanksgiving. I haven't checked if people have accepted it yet, have been working on it, but that needs to be due by Friday at the end of this week. I was planning on bringing that up today, see if anybody has any questions on that, so we'll take a look at that at least for a bit today. But besides that, we do still have a test 2. I had somebody ask about that. Let me know if anybody has some other needs, but my plan basically is to open it up next week during finals week. So we will have a test 2. I'll probably open it up starting Tuesday morning. It'll be due by the end of the day Thursday. So that should be quite a bit of time. That also covers our actual official final exam meeting time, but it is going to be online, so it's going to be the same format as test 1. Almost nobody had any problems with test 1, so again, it'll be more of a review, and I don't think people will find it tough to do it. But technically, it can be comprehensive, but it'll mostly concentrate on the stuff that we talked about since test 1. So that's stuff past logistic regression, where we started talking about support vector machines and ensembles and the unsupervised learning, that kind of stuff. So they'll again probably be like 2 or maybe 3 questions, and I will post it as a question in D2L, but I'll be expecting you to actually do the work in a notebook and upload your notebook at the end of the time period like we did for the test 1. So same format. But let me know if anybody has some needs or some questions about the time on that. But hopefully that should be plenty of time for people to get ready for it and to attempt it. So next week sometime during the middle of the week. So I do have to have everything done by the end of the week next week. So I wanted the test to be done by Thursday. I will give you till Friday to work on the final projects. So don't forget about those. I hope everybody's been doing incremental progress on those. I haven't been checking up on those recently either. But everything that you want me to consider for work that you did on that needs to be submitted before Friday, at the end of next week. So Friday the 13th. That's the 13th next week. So. Yeah, and that'll be it for the class. So I'm planning on, we will meet today. We'll meet also on Thursday for the face-to-face class. I was going to bring up the assignment 5. I haven't completely got back assignment 5 evaluations. I was about halfway through, a little bit past halfway. I'll try to get the rest of those done today. I did go ahead and post an example solution because I did want to maybe mention 1 or 2 things here about the assignment 5. And then after we do that, maybe I'll bring up assignment 6, see if anybody has any questions. We haven't talked about that one yet, so I'll take a look at the questions on assignment 6, and then maybe we'll get into K-means today or talk about it on Thursday. So you do have to do some stuff with K-means on the assignment 6, as well as do some stuff with principal component analysis if you haven't started on the assignment 6 yet. So. All right, so let me go ahead and 2 or 3 things maybe to mention about assignment 5 from the ones that I've gone through so far. So let me just mention those real quickly. Like I said, I think of the ones I've looked through, almost everybody was fine, except for maybe 1 or 2 people having a bit of difficulty, with the task 6. Getting everything quite right on that, on the final ensemble and stacking everything together. So most people did pretty well on doing some small data exploration, even more. Most people did even more than what I showed in the example solution here, but at a minimum, hopefully you were showing like a basic description, and also maybe using like is NA or is null or something to check all the features to see if anything was missing or not. So we didn't ask you to scale the data, this data, so I leave that as an exercise. Maybe if I do this one again in the future, I might go ahead and add that in. If you look at the ranges of the data, like using like a basic describe or some other method, you'll see that there is some difference in the range. So min from 4 to 70 versus some others going, like 1 to 240. And look at the means. You can see we got some things 50, 20, but we got some means negative 4, things like that. So all that says is that maybe, especially since we're using ensembles that can be sensitive to the scale and the range of the data, we might be able to see some improvement if we were to go ahead and do everything that we did in this assignment, but scale the data first before training our estimators. So I haven't tried that. Don't know how much, if any, improvement you might get doing that. So if you're interested, you might try that yourself. So the other thing here, everybody that I checked so far was correctly using like some method like correlation to check the Pearson correlation between the 10 or 11 features and the signal. A lot of people, though, so I mentioned this in class, a lot of people were not plotting the actual things that had the biggest correlation, because negative correlation is just as useful as positive correlation. So the largest one, a lot of people took these out and sorted these, which is what I probably should have done here. But, some of these, if we just look at the signal, the positive correlation, the biggest one was something like 0.17, 0.19. I think the people that were only looking at the positive correlation were plotting this F ASIM, whatever that is, and the FM3 long as the two highest positive correlations, which is fine, but really it's the magnitude or the absolute value that's important. So things that are negatively correlated can be just as important in terms of creating an estimator or predictor. So really you should be interested in the F alpha and the F length here. Those were actually had a bigger magnitude of correlation, even though it was in the opposite direction. So negative correlation, right? So anyway, I don't think I took any points off for that. I just kind of griped at the people that, or reminded people about that. So if you did the one I was asking for, it kind of looks something like that. So everything seems to be down to a floor effect, but in general, the zero, the noise one, the H, tended to be more up here, and the signal was more down in the floored and on the left-hand side. But there's a lot of overlap, so not a clear kind of thing. So, if you did the other two that were the highest positive correlations, you got kind of an X figure. If you were looking at I think it was the ASIM and the M3 long there. So, I guess my only other comment, again, visualizing stuff. If you didn't use some alpha here, or if you did it the other way, it's very easy not to see, like for this one, if you don't use any alpha, and if the zero or the H gets plotted second, it might kind of cover up, and you can't really tell where all of the ones or the gamma are. Right? So a lot of people weren't using alpha, or weren't really using enough. As far as I was concerned, so you couldn't really see both of them very well. Only the one that was on top was the more prominent one. So anyway, yeah, if you have overlapping stuff, it's usually a good idea to play with alpha or other things, just so that you can see everything, all the two different categories in this case, and one's not on top of the other, kind of hiding the information that the other one has. So. I had one person, one or two people used a stratified split on this one. So if you used a stratified split on your implementation here, of course you couldn't get the test to pass. So let me real quickly show. I mean, the task 2 should have been very simple. I mean, all I was looking for was just reuse train test split, but use it twice in sequence. So use it once to first get the training data, and all the rest is something else, and then split the rest into validation and test data. Right. So I think almost everybody had that right. But as I started saying, one or two people were using a stratified split, which is actually a good idea here. It didn't take any points off of that, even though they were not able to pass the test if you do it that way, because I was expecting the data to be split in a particular way. So, my tests were checking that, after your split, you had a particular item at index 0, that kind of thing. So I just mentioned that because I thought it was a good idea. Anytime you have data that's skewed, it's often a good idea if you're splitting it to use some sort of a stratified split to stratify it on the label. If you don't, especially if it's really skewed, you might end up with a split that has none of one of your labels, right? So in this one, it wasn't too badly skewed. It was about 2/3 was the noise, was the signal. I can't remember. I might have that backwards. So 2/3 was one of the labels and 1/3 was the other, right? But even with that, you could end up with a bad random seed with a bad split, and you get a training set or a test set that doesn't have very many of the 1/3. It has significantly less. Right? It's not going to be a problem usually until you're you're really much more highly skewed. So once you get to something where only 10% or 5% or less is of one class, then you can very easily end up with a case when you do a split and you have very little or even no examples of your class that doesn't have a lot of examples of it in the original data, right? So anyway, I thought I'd mention that because that is a good idea. Anytime your data is skewed, you might want to consider do that stratified sampling like we talked about. And so sample stratified on your target label, so that you make certain that you keep the same representation of approximately the skewedness in your training data and your test data. Right? Okay. Besides that, I was glad to see, I think, of all the ones that I've looked at so far, everybody was doing fine on creating a voting classifier, was passing the test, and we're correctly accessing the trained estimator. So, I guess the hint was hopefully enough here. You can actually get access to the untrained estimators and the trained estimators. If you use the untrained one, you get kind of results that seem strange, I think. I should try that, see what happens. This is what I got. This is what most people got. So you should have probably seen something that, so if you evaluate it on the data you originally trained with, of course, this should make sense if you've understood the class so far, because the basic decision tree will always overfit, will almost always overfit. So you get exactly perfect accuracy on the data it's trained with. But in general, you get higher accuracy mostly for most of the rest of these on the data it was trained with. But you should have seen on the validation data that normally you got about 0.81, 0.82 for these, for the best ones. So 3 of them, almost all of them were getting about 80. But you got around 81.5% for 2 or 3 of these. But yeah, I think everybody was correctly evaluating these on the training and validation data like I asked for, that I've looked at so far. Hopefully everybody, the rain ones, everybody was doing it, as well as also looking at the whole ensemble, so see the performance on the ensemble by calling the score or accuracy or predictions on the voting classifier that was actually returned, instead of the individual estimators inside of the voting classifier. So in this case, I mean, it may or may not be significant, like I talked about, but you should have seen that maybe there is about a percentage point improvement on hard voting over the best base estimator. So we only get about 81.5%, but you usually get 82.5 or 82.8%. For the hard voting. Likewise, I think everybody implemented the soft voting correctly. So, all that entailed was correctly using the third parameter when you create your voting classifier to use soft or hard voting. Oh, and also, I guess, you were told to do this, but also making sure that all 5 of these could support getting the probability predictions if you ask for it. So the only one that's an issue for is for the support vector classifier, that you have to specify the probability is true in order to use the soft voting. Right. But anyway, again, I mean, soft voting, this may be significant, may or may not be, but it looks like it's getting a little bit of an improvement. So going up from close to 80, just under 83 to 83.5 or so on the validation data that it wasn't trained with. Yeah, if you weren't, I had 1 or 2 people that weren't exactly getting that. We're getting strange things there. So, if you weren't getting approximately that, you might want to go back and check what you were doing with your fit or something else there. All right, and I don't know if I have anything to mention on task 4. Oh yeah, I did it actually. Probably the most common problem, and I can take off a point or 2 for this, is when you plot the receiver operator characteristics area under the curve. There's lots of ways to do it, but you have to use, the estimates of the probability when you do that. If you don't do that, you don't actually get the area under the curve. You get the wrong thing there. So if you had straight lines on this, you were just using the predict of 0, 1 instead of using the probability estimate for the prediction. Right? So yeah, you should have gotten something nice and kind of, it's a little bit jaggedy, but kind of for the first one, if you do the area under the curve for the tree that I asked you to do for task 4, it looks like this, and you got something like a 93% area under the curve on that one. Okay, I don't think I ran into anybody that had a problem with the task 5, the stacking the data. There's lots of ways you can do it. So here's an example of how you might do it. So and I saw some people doing it where they were adding in the stack incrementally, which I didn't really personally like that much. So here in this one, basically we use the estimator to give the predictions for all of them. Just keep that in a regular Python array, and then use the HStack. So this everybody I think that I've checked so far was using HStack to stack these horizontally, and that does most of the work really for you. You just have to get your estimates from each of the estimators that you have, and then somehow use HStack to create your stack for your inputs here. But yeah, I don't think I saw anybody have a problem with that one. Like I said, probably the one where the most points came off was some people were doing some things wrong on the last task here, so pretty much they gotten it up to that point, but we're losing the kind of the thread of how to do stuff once we got down to here. So basically, really quickly, for any of those, if you were having some problems on this last one, it should look something like this: the implementation of the task 6 function. So you should reuse. Hopefully, I was checking that for everybody. I did ask you to reuse the work that you did to create a voting ensemble and then to stack the data. Right, so you should have been using the one just to create a new voting ensemble, using soft voting. Did I specify that? I can't remember. But soft voting is probably a little bit a little bit better than hard voting, like we saw when we did task 3. So it would make sense to use soft voting to try to get the best performance here. And then whatever data that we're given for training. You have to be careful. So whatever the ensemble was that we just create, you need to use that to evaluate your data on the validation data. Hopefully, I was checking this as well. So you really should be training with the training data, but stacking the validation data and using that to train a new, what our textbook calls a blender, right? Which is basically taking all of these as base estimators, and so the stack data is the output from the base estimators for the validation data, and then we train the support vector classifier to act as a blender on that stack data. So yeah, it should look something like that, and then you just need to return the support vector classifier that you created and the voting ensemble that you created a second time here. Now, to evaluate these to evaluate that return, one common problem, some people. If you're not paying attention, or if you're, still a little bit fuzzy about using functions and stuff, I know a lot of people were getting the test to pass, but then weren't using the blending estimator or the voting ensemble that was returned from their task 6. It was using something else that was created before up there, like using the voting classifier that was named like VC or something from task 3. Or using, I can't remember, but doing something else with instead of the blending estimator. So anyway, to evaluate the performance on the blender, you do have to, if I want to evaluate it on any data, I have to stack it up because I don't have the correct input for that blender. The blender is expecting the outputs from the base estimators as inputs. So you have to first reuse the create stack data on, if I want to evaluate on the training data, I have to stack my training data on all the base estimators, and then I can use that stack data to evaluate the accuracy on the training data. Or I can do that with any set of data. So you can do that on the training data or the validation data. If you do it on the validation data, compare that to what we had for the for the voting classifier. So we're getting about 0.85 here for our blender, where, if you did it like I did, again, most people I checked were getting about the same result. So again, it seems to be getting a bit of an incremental improvement, which is kind of nice. May or may not be significant, but we're getting maybe about 0.83, 0.84 for just the regular soft or hard voting. And the blender is maybe getting 0.85 or so on the validation data. Or at least that's what I saw. Right. But like we said, though, this is a little bit unfair, because we're actually leaking some information. Even using the validation data, we used the validation data, or you should have used the validation data if you implemented the function correctly to create the blender, right? So the 8.5 is kind of unfair here. So the thing that we really should be comparing to our soft and hard voting on task 3 is how it did on data that we never used on any, on any step when creating this stacked ensemble, this blended ensemble here. So that was why we were supposed to use the test data, but we still get 0.84, which again I think is a little bit of an improvement over what we were getting just using a regular voting ensemble, which is kind of nice. All right, and then this one, right? Again, some people that were doing it wrong on the first time I asked you to plot the ROC curve, probably did it wrong the second time. I only took off 1 or 2 points for both. I mean, total, not each time. So. But yeah, this one kind of had a little bit. I could tell when it was doing exactly the same thing that I was doing, so you could see it kind of going this way and then coming up there. Okay, yeah. So it's a little bit longer than I was thinking I could take. Anybody have any comments or want to know anything about the assignment 5? Yeah, we're good. Okay, but I did post that. If you do want to get more into detail on that, there's some examples you can look at, especially some of those people that had problems on the last task 6 might want to go back and review the example implementation that we had on here. So, okay. So, like I said, let me go ahead and bring up assignment 6. Let's discuss that for a bit, see if anybody has any questions about that. I did get this posted before Thanksgiving, so it has been up there, but I forgot to post an announcement about it. Okay. So I'll talk a little bit about k-means today. We talked about reciprocal component analysis a bit before we went on Thanksgiving. I can answer questions about that. So for both of these, the heart of the assignment 6 is kind of implementing by hand some of the steps for k-means and for reciprocal component analysis. Okay, so we really haven't talked about k-means yet in class. K-means is relatively simple. So let me just go through these. So we've got kind of the usual. It's the same format as the previous 2 or 3 assignments. So you have to complete some functions that are in the assignment tasks source subdirectory. It'll run some tests to check that you're doing the basics that are expected. For this one, we again go back to, we've got some data sets in the assignment, one for the k-means data, and one for the PCA, component analysis data that you're supposed to do. The k-means data has, we're going to, in the assignment, try and cluster it into 3 clusters. There's 3 kind of obvious groupings here. So using k of 3 makes sense here. So yeah, if you load the data, I did ask you to do a plot like that. You should be able to recreate this plot with that, and recreate the plot with the initial location of the centroids that we'll be using for the testing. They should end up at those 3 locations here. So this will be kind of going into a little bit of what I was going to talk about today in class as well. So we're kind of getting started on talking about k-means here. But the algorithm for implementing k-means is relatively simple. So in fact, I mean, that's kind of what we're doing. We're implementing the basics of it in this assignment here. So k-means is another example of a unsupervised learning method, right? So PCA was dimensionality reduction, so we would do that on data that's not labeled. Same for k-means. K-means is a clustering. Okay, so clustering is very useful in lots of contexts. So if you take some data and you don't know anything about it, you might want to ask, are there some obvious groupings, right? So those become sort of like the classes if I'm going to do a classification task, right? So clustering allows you to potentially identify the classes that I could then maybe make a classification model of, right? To try and predict which of 3 classes some data point is in, like in this data here, right? So, don't get k-means confused with k-nearest neighbors. So k-means is an unsupervised clustering, where the k-nearest neighbors is a supervised learning. So we can use it both for classification and regression. In k-means and clustering, what we do, normally we just start by selecting some centroids, so what I'll call centroids at random, to be the initial centroids. Okay, and what we mean by a centroid is, like we show in this figure, it's really just a location, right? So if I have 2 features, a centroid is just sorry, if I have two features, x1 and x2, if I want to try and find 3 clusters, I would select 3 centroids at random. Here. So normally what we do, if you look at the way that k-means and scikit-learn works, the default is I just select 3 points in my data that I'm clustering at random to be the initial centroids if I'm using a k of 3 here, if I'm trying to find 3 clusters. Okay? But you can also just randomly generate, which is kind of what we do first here. In this example. So anyway, the initial centers are just some points in whatever dimensional space that you have. And then the basic algorithm for k-means is we first, so given the current set of my centroid points, so if k is 3, I've got 3 centroids. I'm going to assign each one of my data points to figure out which of the 3 is closest to. Okay, so this first function you have to write, the find closest centroids. Basically, you look at every point that you have in the data, and you calculate the length between each point. So if I'm trying to figure out which centroid to assign this point to, I just calculate the length between it and that centroid, and that centroid, and that centroid. And of the ones identified, probably that one is the closest, right? So you can just use simple Euclidean distance is the usual thing that we do. We just use the regular definition of the distance or the length. Right? So given that, this point, we would assign it to be to that centroid there. Right? Whereas, like this point here, if you look at the distance, would be closest to that centroid and so on. So every one of the points is going to get assigned to whichever is the current centroid that's closest to. So that's what the find closest centroid does. So that's the first function that you have to write. So the result of that, we say as returning this little C here. I think I got this from the textbook or from some other example here. But you can also just think of that as the label. Okay, so so normally the way I think of it is, we just call these as, this is label like 0, label 1, and label 2. So all that's being returned from find closest centroid is just a vector of the label. So that you could use that if I wanted to build a classifier. I could use that as the training labels then. The result of calling your find closest centroids. All right. But anyway, hopefully that's clear. And if it's not, the test should make things relatively clear for you. It shouldn't be too tough to do this. It is fine to implement these. There are ways to vectorize these functions for the find closest neighbor and the recompute the centroids. But I didn't make it a requirement for this assignment. So you might want to just go ahead and do a non-vectorized solution first, and then if you want to, you can figure out if you can vectorize it. All right. Everybody hopefully knows what I mean by vectorized versus non-vectorized at this point in the class. So you can just write, for example, to find the closest centroids, you can just loop over each one of the data points, calculate the length between it and each of the three, and just figure out which one it's closest to, and then use that to assign the correct label in the C that you're going to return from calling the function. Okay, and then really k-means is just an iterative algorithm. So what you do is after you assign, basically after you label every one of the points to which centroid is closest to, we recompute a new set of centroids. Okay, so I wish I had something I could draw up on here, but like for these initial 3 points, basically everything, everything that's about where I'm indicating right here is going to end up being closest to that point. All right, so all that and all that. Now, so everything that ended up being in that centroid, we would recompute a new centroid for that, right? So just the points that were assigned to this centroid, we compute a new centroid. And computing a new centroid, again, we throw some formalism for you, but it's very simple. It's really just the average. So if you take all the points that are in centroid 0, for example, we just want to find the average of each, so you basically just sum up all of them and sum up each one of the features, right? So this is just sum out. If we have 2 features, then this is going to be a 2-dimensional thing. We're just summing those up and then averaging them, right? So that will compute a new centroid for all of the points that were assigned to that label or that centroid. Right? So the effect of that is that if you plot these, you would see that it would move all these. So you first assign every point to the closest centroid, then you recalculate a new centroid. If you keep iterating like that, eventually things will converge. They will settle down, and the centroids will stop changing because from one assignment, from one changing computing of the centroids to the next one, none of the points would change to a different centroid or to a different label. So once that happens, it'll converge and the centroids will stop moving. All right. Although in this assignment, so it's normally, if you look at the real implementation of k-means and scikit-learn, the stopping condition for the loop is it'll stop once the centroids have converged. So once they stop changing, or once the labels, from one iteration to the next, if we end up with the same C with the same labels, we would stop at that point, because at that point the centroids aren't going to change, right? But for this assignment, it's relatively easy to implement that, although for this assignment I just asked you to iterate a fixed number of times. So the second, or the third function that you have to implement, one of the parameters that we pass in is the number of iterations to perform when you're doing this here. Right? But again, if you're doing this assignment, if you're interested, it's pretty easy to then generalize that. So to stop when convergent happens, you just have to keep track of the previous set of C labels that were assigned, and then we get a new set of C labels, and then if any of those have changed, then you're not going to be converged yet. If any of those labels have changed, then the centroids will change position. But if from one iteration to the next, if all of the points were assigned to the same place, then the centroids will stop changing, right? And you can stop at that point. So, the final function that you have to do for the first task is to write basically that pseudocode. So you implement the k-means cluster function. It should basically just have a loop. You are required to reuse the previous two functions. So inside of the loop, you're just going to be repeatedly finding the closest centroids, and then using the first function here, so calling your find closest centroids, and then calling your second function to recompute, so to move the centroid, the centers, based on to the labels that were just given. And again, right, just do that for a fixed number of iterations for your first implementation. So 10 or however many iterations are specified in that third parameter. You do need to be parameterized correctly, though, right? So you should be able to handle not just a fixed 3, k is 3 centroids. So that means that whatever k is passed in, that will affect the number of initial centroids that you select at random here. And that would affect what the range of the labels can be. All right, so when k is 3, then your labels are going to be either 0, 1, or 2. If k is 10, then your labels in the C there can go from 0 to 9, so on. So, and it is discussed here, but there is you're asked to randomly create the initial set of centroids, and in order to get this function to pass, it kind of tells you how to do this. All right, so using Python, you should go ahead and use the random choice method. Before you actually get into the loop, you have to select, you have to set up K centroids initially, right? And we're going to do that the same way that scikit-learn does it. So we're just going to take your input data and select, if K is 3, we're going to select 3 of those points at random. So the way to do that is you can use random choice. So if X has 1,000 samples, you can ask random choice to choose 3 indexes at random from 0 to however number of samples that you have, right? Make certain that you're calling random choice where you ask it to give you sample the centroids without replacement, just to make certain that you don't end up randomly choosing the same point as the initial centroid for 2 different locations. If you did that, you would have some problems with the algorithm. The 2 points would start out the same, and they would never change, or it would depend on how you're assigning your label. So it would be the same distance to both of those points if they start out the same place. So anyway, just be careful about that. So do the choice without replacement. All right. I don't know if that's helping or if that's clear enough or not, but yeah. So you do have to do that. So that is before the loop, and then inside the loop, you pretty much should be relatively simple. If you have the previous 2 functions working correctly, you'll just be repeatedly calling those 2 functions to iterate your centroids, and then return those. You return the final labels. That's not true. Yeah, so I made it a little bit more complicated so that we could plot this stuff here. I ask you to return back also a history. So the location of the centroids at the first iteration, the second iteration, and so on is what should go into this history here. So that you don't normally get that back. For example, if you use the k-means from scikit-learn, you just get back the final labels, the final C of the clusters. But yeah, with the history, you might find this a little bit difficult here. I didn't give you a lot of hints, but I want you to recreate this figure. So, and if you're generating the, so here for this task, we're going to do it where we use 3 centroids. So we start with 3 randomly selected centroids. So notice, for example, here maybe it's a little bit tough to see on here, but like for my one that I labeled as class 0, the red one, it initially picked that point there. So that around that green circle, that was the random point that got chosen. And if you implement this the way it's described, you should get exactly the same results here because you also are supposed to set the random seed. So you should be able to reproduce this figure and the history. Right? So notice, this was the initial point for class 0. That was the initial point for class 1 out here, and that was the initial point for class 2 here. And as we iterated, so after the first iteration, this centroid moved from here to there. That one moved from there to there, and that one jumped up to there. Right? And eventually, after 10 iterations, these points basically, all the blue ones here, you're supposed to also, indicate the final labels of the original data that result from doing your k-means clustering, right? So all the blue triangles are closest to that class 2 centroid. All the red circles are closest to the class 0 centroid there at the end of 10 iterations. And all those green squares are closest to the class 1 centroid there. Okay. Okay, yeah, so I think that's good enough on the k-means. Let me know if anybody has any questions on that. I wouldn't I wasn't thinking about spending that much time on this, but really, that's the basics of k-means. So maybe on Thursday I'll come back and look at our lecture notebook material on doing the k-means. But that's, you're basically, when you do the assignment, you're going to have to understand how the k-means clustering works in order to write those three functions and be able to reproduce this history for a k equals 3 cluster here. Okay, and then I don't know if people will find the task 2 to do the PCA challenging or not. I don't think people will, actually. We're doing something similar again. Basically, we're going to step you through re-implementing principal component analysis by hand by using the basic linear algebra singular value decomposition function and the other things you need to do in order to perform a PCA. So we talked a little bit about this before Thanksgiving. But again, we ask you to write like 2 or 3 functions. So write one function to normalize the features. We could have just had you reuse the function from scikit-learn. So, but yeah, we ask you to kind of by hand normalize. So the result of this function here is if you have a set of data x, which in this case is going to have 2 features, but I don't have a plot of this. I did ask you to load the data and plot it again. But if you normalize the data, you should end up afterwards that if I have 2 features or however many features, each one is going to have a mean of 0 and a standard deviation of 1. Right? So that's described here, but you can do it relatively easily. So you have to calculate the mean and the standard deviation of each of your columns of each of your features, and then you have to divide, you have to subtract the mean in order to center it to 0, and you have to divide by the standard deviation to normalize it to have this a standard deviation of 1 for each one of the features. So yeah, this is a necessary step. So if you're using, hopefully, we mentioned this when we talked about PCA. If you're using scikit-learn, it'll do the normalization for you, so you don't have to worry about giving it normalized data. But yeah, if we're going to do it by hand, we do have to make sure the data is normalized first in order to reproduce the results that we might get from scikit-learn. So I don't know if I emphasized this last time when we talked about PCA enough or not, but the actual singular value decomposition is done on the covariance matrix. So the next step after we normalize the data is we have to calculate this covariance matrix. All right? I mean, this is really similar to we're doing kind of the same thing as calculating the covariance between features, like I had to do for this assignment that we just finished here for the first task, right? That's kind of really what the covariance matrix is. So we can calculate the covariance matrix by just taking the data and doing a matrix multiplication times the transpose of itself. And then we divide by the number of samples in order to average that. And that should give us the covariance, the amount of similarity between each feature and every other feature that we have in the data. So, I mean, that's really what's being done with this covariance matrix. Oh, I'm sorry. Yeah, I asked you to do all the steps here. So that's the first step. You actually you have to do what? 3 things to implement PCA by hand. So you have to normalize the data. So you should reuse your feature normalize, call that function to normalize the data that's given here. The next step is to do the covariance matrix that we're talking about. So if it's, I sometimes, I think I mentioned this last time when we talked about PCA. This symbol is used for summation and other contexts, but it's really just a variable here, right? So just think of that as like S or some variable rather than sigma here. But that's just representing the result of calculating the covariance matrix. And then after that, you just have to perform a SVD, so your value decomposition, on that covariance matrix. Right? So to do that, you should just reuse the SVD function from NumPy's linear algebra library, right? And that will return basically what you need to return from the function. So we just ask you to return. We don't really need the V. We just need the U and the S from the singular value decomposition. So we ask you to return those. We also ask you to return the mean and the sigma vectors from doing the normalization step. I didn't mention those, but yeah, for the first task, you're actually returning not only the normalized data, but the mu and the sigma for the data before it was normalized. So that should be being returned from the first function that you do for this assignment here. So I think, if I remember, just to let you guys know that if you implement the PCA correctly, you shouldn't have to do anything on this step here. So it will use the values in the U and the S and the mu and the sigma to plot the computed first and second principal component. Okay. So you should end up, if PCA and your feature normalized are working correctly, when you run this cell, it should recreate this figure. Right. You might want to see if you can figure out how it's doing this. So just as a hint, so note what we do here, we use the U, which is actually going to be a vector. It's actually going to be an array, but we pull out the first column, the 0th column. That's going to represent a vector for the first principal component, right? And then we use that to plot. So that U1 is what we use to plot the arrows, although we take the U1 and we multiply it by some other stuff in order to scale it, rescale it into the unnormalized original data, right? But so that U1 that's pulled out here out of this U that's returned from your call to PCA here, we use that to calculate what the direction and the length. So the length represents how important that component is relative to the other components. Right? And the direction was the actual direction of the first principal component. So remember when we talked about PCA, that is the direction that has the most amount of variance. So it keeps the most amount of variance of our data that we're trying to reduce in dimensions here. And for this assignment, again, it's only 2-dimensional data, so the second principal component is going to be, there's only one choice for that. It has to be at a 90-degree angle to the first one that we find. But anyway, the U2 is calculated by doing the same thing we did for the U1, but we just pull out the vector that's represented in column 1 from the U matrix, do some manipulations in order to represent the magnitude, the importance of the second principal component, and plot that as an arrow here, along with the original unnormalized data. Okay. Oh, and I did actually throw in two more things in order to do actual dimensionality reduction, and then reprojection back after you reduce the data. So the last two functions for the task 2 on the principal component analysis is one to project the data down into one dimension is all we test here. So projecting it from 2 down into 1. And then to recover the data back into two-dimensional space. Okay, so I mean, these two functions won't be very complicated. You just have to, in fact, we give most of what you need to do as an example before the function there. So to do the reduce, you're really just selecting some number of columns from that U matrix. So that's not everything. That's like the first step here. But we also do give an example of doing this in the lecture notebooks. So once you just take this, you have to actually do basically a matrix multiplication of that times the original data to project it down into your reduced dimensions. Okay, so I think it's as simple as that, though. So you calculate this, and then a single matrix multiplication will get you the z that you need to project it down in one dimension. And then the last one to recover just kind of does the opposite. So you'll be doing pretty much the same thing, but in the reverse here. So if you do this correctly, you shouldn't have to do anything for the last one, but it will reuse the things that are returned from projecting and recovering. So should reuse the X recover. Yeah, from the X, just trying to find it here. So yeah, when you reduce down and then you recover, basically these are the locations of the red points that are plotted here. So again, you shouldn't have to do anything if those functions are working correctly. The result will be, though, that going in and then recovering back, you'll get the red things here, and then the rest of this code is just plotting the original data and also connecting up the projections of each one of the points to the one-dimensional location where it's projected. Right. So I encourage you to look at that, see how much of that you can understand, how it does this, how it shows the resulting projection, assuming that you can get it working, get it correct in there. All right. So yeah, I wasn't planning on maybe doing the whole class on that, but that's fine because we kind of also got started on the k-mean. So that's basically it on the assignment 6. So So let me know if anybody needs anything clarified on that. So that assignment 6 is due this week, due by Friday. It's our last assignment. I don't know if everybody came in after I announced this, but just to say again, so, we still have the assignment 6 due on Friday this week. So make certain you get that finished up. If you haven't started on that, you probably really should get started on assignment 6. I think, I don't think it'll take most people as long as the previous assignment 5, but maybe. But also besides that, don't forget we still have some other stuff. So we do have the test 2. I talked about that. I'm going to have my plan right now is to open that up from Tuesday to Thursday. It'll be the same format as test 1, so it will be timed. There will be 2 or 3 questions. There'll mostly be probably some stuff with like PCA, support vector machine, something like that. Where when you start the test, you'll be given the questions, but I'll be expecting you to have a working IPython notebook and to give your answers, to write some code to answer the questions and then submit your work within the time limit for the test. So, but yeah, the same format as the previous one. You'll have to attempt that and finish it sometime on Tuesday, Wednesday, Thursday of finals week next week. So, and it's not in class, so you do that online. We won't be meeting next week, so Thursday will be our last meeting for the class. So. And also don't forget the final project. I keep trying to remind people about that. I haven't been checking. Hopefully people are making some incremental progress. I've been doing stuff on that, right? So I would hate to find people that haven't done anything and then give me a bunch of commits here on the last week or something like that, right? So it'd be better if you've already been doing some stuff. Have been doing commits regularly since we started on this about halfway through the course. So. But for that final project, all work does have to be in by Friday of finals week. So I won't be able to look at anything that comes in after that. Right? So anything you want to be considered, you need to post that by Friday. I guess by Friday midnight at least. So. Yeah, so as long as it's sometime Friday, I'll still be able to look at it, I think. I'll have to be doing stuff on Saturday, Sunday, and Monday, but yeah. So. All right, yeah, so that's it. I'll let you guys go. So I am planning on meeting on Thursday. We'll talk a little bit deeper about K-means, see if anybody has any questions on assignment 6, but otherwise, that will be it. Okay.